Good morning, everyone. Hi, guys. So the professor is not going to be joining us until Monday. And before we start with the lecture, let's get done with the logistics. So how is homework 1 going? Are you done with the part 1 yet? No. Have you at least started part 2?
Yeah.
OK, so where exactly are you stuck in part 1?
It's running out of GPU RAM.
Part 1? Part 1 doesn't require the GPU.
Oh, are we talking about part 1? Okay.
Yeah. So what do you mean by part 2 running out of GPU? Like, you have your AWS instance, right?
Yeah.
And P2X large should be sufficient to get through A for the homework? Yeah, even if you load it, you should be able to do it. Like, it's just a 3 GB data set, right?
But when you add the context, if it's a large context, it goes up to like 60, 70.
So probably you should be looking at how you're batching. You should not be taking the entire data set at once, but just make sure that you only have the required data that you're training on the GPU at that time. You don't have to run through the entire data to train it. So we can make a post on it, but apart from it, do you have any other problems?
I think the batch norm specification took so long just to figure out because the assignment doesn't really describe like how that should work.
OK. So actually, batch norm was scheduled to be today's lecture. But since most of you coming here already have that background, we kind of thought we can just give you a derivation and you could implement it.
Yeah, just like maybe like a description of where it should fit in. It's not even clear. Some of the arts posts help, but not for the lecture. But
OK, so exactly for this reason, we extended the initial deadline. We don't have the 21st deadline right now. You can submit it up till 24th.
so both parts.
Yeah, exactly. So you got 3 extra days for it. I think it's fair, right? Yes. So initially, the deadline for homework 1 part 1 was 21st. Now it is 24th. You don't have the early submission deadline.
You said homework part 1 is 24th as well now?
I'm sorry?
You said homework part 1 will move back to 24th?
Yes. Both parts on 24th.
So it's due, so right now we have part 1 due on 24th.
Yes.
Midnight?
Yeah.
And part 2 is still due?
Both part 1 and part 2 are due on 24th. OK. So we're going to be talking about optimization today. This lecture will be particularly important because you just started working on your part 2 and learning some tricks on how you can make your network converge faster would really be beneficent. So a quick recap. So we've looked into how gradient descent works, the backprop, the forprop, use a divergence function to compare the obtained outputs with the expected outputs, and then you propagate that error back through the network. And then you try to minimize the function by updating the weights and biases. And finally, you keep iterating the training until you get an approximate function which gives you optimal results. Yeah. So one of the issues that we encountered was when you use a when you try to train your network and you have a fixed learning rate, the step size is really important, right? There is a chance that your network starts diverging because you have a fixed size and you have a lot of dimensions to train on. So it might be possible that a step size that is good enough for a dimension in X is not good enough for a dimension in Y. So for that, we talked about momentum methods where we keep a track of all the gradients that we have from the past. So we keep tracking the gradients, and based on the running average, we take our next steps. We spoke about the Nesterov gradient method, wherein you look ahead. If you're in a state currently, you look ahead, you see what the gradient is, and then based on that gradient, you take a sum of the vectors and you go in that direction. So this is a smarter way, but it doesn't really work in every case. So topics for the day is we'll be talking about different ways in which we can train a neural network. Basically, the way you can sample it, stochastic gradient descent, where you can just sample using a single samples, and you can go through the entire data set, updating one sample at a time. And then you have your batch gradient descent, where you just take the entire data set as a batch, and you update all of those samples. There are 4 of those samples. And then you have your mini batch gradient descent, where you take small batches, and you make incremental updates to your weights. So this has proven to give us better results. We'll look into why. So firstly, what exactly are we training? So suppose we have a function y equals f of x. We are trying to model the function f. So we have the inputs x and we have the outputs y. So the function can be estimated to look like this. This might be the optimal. This anyways are 2-dimensional, but suppose it looks like this. So initially, when you initialize your random weights, you can assume your function looks like this. So all you have to do is try to fit this red curve into the blue curve. You have to minimize the error, the area that is between these. So how you can think of it is, you have a cloth, and you're trying to shape that cloth into a certain shape. You can pick points, and you can pull and push points below until you have the most approximate representation of the function you're looking for. So this is how you can keep updating it. So how does number of samples affect this? So if you're trying to update the function using a single sample, so you'll be picking one point. You'll be picking at one point, right? So it's really sparse. But in order to approximate a function, you really need to have a lot of samples, so that you don't have to approximate any curve between 2 samples. Are you following me? Is that fine? Thank you. Okay. So see, these are the points. You hold one point at a time. This basically shows how stochastic gradient descent works. You update one sample at a time. You pull one point on the function up, or push it down at a single time. As you can see, this might be a really slow process, because you have to iterate through the entire data set to have one epoch. So that is the reason we look into methods like batch and mini-batch gradient descents. So randomization. Why do we have to randomize data before we train the network? So there have been a couple posts on Piazza where people ask us, why do I have to have an IID, statistically independent samples? So basically, if you're sampling through the data set exactly the same way every time, what happens is there is a probability that you have a cyclic behavior for the network. So you update the network exactly the same way every single time. So when you're updating it the first time, the network optimizes here, and then you get to the end, it slowly moves away. So this kind of gives rise to a cyclic behavior, which is not right, because the network always remembers the last update that you made to the network, the latest updates. That's the reason we have to go through it randomly. Get it right? So if you keep moving on a forward pass and you update it, it looks like this. And when you keep iterating it, it just exhibits the same behavior again and again. So let's take another example to differentiate between stochastic and batch gradient descent. Yeah.
What do you mean by cyclic behavior?
So the network doesn't really learn any new things. It just keeps moving between the same function. So initially, it learns some behavior. And then when you move through the samples, it learns another behavior. And when you have the same thing again and again, it sort of overfits and doesn't learn anything new. So it moves between predicting the samples that you initially gave and then the samples that you gave to the network towards the end. So if you randomize the network, there is a high probability that you have a more approximate curve. We'll get to that in a while. So yeah, so the difference between a batch and a stochastic gradient descent. So what happens is, yeah.
So you're saying that this incremental update is stochastic gradient descent?
No, incremental updates is updating the network in steps. So gradient descent is just a concept. Stochastic is taking one sample at a time. So we'll just get to that in a second. Yeah, so what happens when you try to train the network with a batch is you have the gradients of all the weights, so for all instances. And then you try to average based on all of those gradients, and you move in the direction which is average, right? Whereas if you have a single sample, you move in the direction which makes the network learn only that single sample. So for in a case where all of those samples are unfortunately the same, suppose you took a sampling where all of those samples are very similar to each other. So a stochastic gradient descent will be updating the network t times. So if you have t samples, you have to iterate and update it t times, right? Whereas in a batch gradient descent, you just have to update it once. You take the average of all the gradients that you have for different instances, and you update it once. So batch gradient descent is way faster than stochastic gradient descent, but there are a few differences. We'll get to that. So you see, a batch gradient descent basically updates it in a single go, and SGD takes t computations to do the same thing. This also works with data which is very similar. You don't have to have the exactly the same data to do it. Even if the data is slightly different, this still applies because the gradient is still going to be in the same direction. Okay. So learning rate. So how do you choose the learning rate? So if you have a learning rate which is way too small, then the network never converges, right? So you're always stuck in optimizing those little steps that you never get to the optimum. But if you have a large learning rate, the network tends to become divergent. So it never gets to the optimum because the step size is too big. So here, there is another issue. Yeah, so the learning rate also depends on how accurate your network is at classification. So if your learning rate is too high, the network always tries to minimize the error in a way that all of those samples are. I'm sorry. If you have a smaller learning rate, all of these samples are very well classified. So it is kind of a bit of overfitting, but we'll look into it. So stochastic gradient descent. How we just spoke about how the step size is a big factor in teaching the network how to model the function. So basically, there have been a lot of studies where the optimal comes down to this. So the learning rate should be inversely proportional to the number of iterations that are taking place in the training. So if you are training the network from a point over 10 epochs or something like that, so initially you start with the larger learning rate and you keep decaying it until a point where you don't have to worry about the learning rate being too big to step out of the training becoming divergent. So there are two conditions for this. Firstly, you should be able to explore the entire space. So the learning rate should not be bounded. You should be able to move around freely, but at the same time, it should be convergent. So that explains the first two equations here. Firstly, the summation should be infinite. That is, you can explore the space and look into different areas where you can where the network can find an optimal, and then the network should be convergent. So looking at this graph basically tells you how well different networks converge. So the red line shows stochastic gradient descent, the convergence, and the vertical lines shows the variance. You can clearly see that stochastic gradient descent is very quick at updates, but at the same time, it doesn't really converge to an optimal. Like you can pick some really hand-picked, cherry-picked example and show that SGD works better, but it is not true in all cases. So people usually tend to go with batch gradient descents because mini batch or grouping gradient descents basically because it is more stable. You do an update over a large samples, whereas stochastic gradient descent, you'll keep updating the network at individual points.
Question.
Yeah.
So in this graph, every vertical line representing a convergence here.
I'm sorry?
In this graph, does every vertical line represent a
No, the vertical lines represent the variance. The curve represents the convergence. So it is the error versus the training time. So how long does it take for the network to converge? So when we talk about the function, when we talk about modeling it, we kind of assume that the number of samples we have tend to give us a really good approximate of the function that we are trying to model. But it is not really that case, obviously, because the function has too many sample points, and you just can't do all of it. For example, if you're trying to teach a network to classify images, MNIST dataset, you have, 784 dimensions. And each dimension can hold up to, 256 values. So it is 256 power 784 values that you have to sample to get the perfect function. But that's not the case. That's really difficult to do. Therefore, we have an empirical risk involved. You basically tend to look at the expected value of the error function, the divergence. So you run a lot of iterations to get the average, and you tend to say that the average shows the approximate function that you're trying to model. Yeah, so why do we care so much about the number of samples again? So the variance is inversely proportional to the number of samples here. So if you have a lot of samples, the variance is low. If you have few samples, the variance is going to be high. So any small changes in the training can make a lot of can have a lot of impact on the model function. So having a lot of samples makes it easier for you to be sure about how approximate or how good your model is. Yeah, so so what exactly do we mean by error? So let's look at two of these graphs. Blue is a curve that we are trying to, blue line is a function that we are trying to model, and red is where we are. So the area that is in between these curves is the error. So basically what we're trying to do is we're trying to reduce the error in between these by using the sample. So you have a sample, you sample at different spots, and you try to move in a direction where the error is minimized. Yeah, so basically having more samples, again, it's the same thing. Having more samples would lead to a better training, and you'll have much more confidence in saying that your model is approximate to the model that you're trying to produce. So if you have a single sample or very few samples, any update to the function with these samples is going to sway the entire network in different directions, right? So you don't have, suppose you have this function, you have a sample here and you have a sample here. So everything in between that sample is approximated. So if you have more samples, you don't have to approximate it. You know exactly what the network should output at those inputs. So you don't have to just extrapolate anything in between those samples. So we spoke about stochastic gradient descent and the batch gradient descent, but there is another method which is called the mini batch gradient descent, which is what we all use. Basically, this is a smaller version of the batch gradient descent. Basically, we take in a small set of samples, and then we keep iteratively training the network on these. So what happens is the sample that you took is a random sampling, and basically this is supposed to give a random. This is supposed to represent a random distribution of the dataset that you already have, which is not the case, but yeah, that is the concept. So you have a random distribution of your dataset, and you pick small samples randomly, which should be the expected value of the random distribution. But once when you keep iteratively training it, you can expect that the network learns multiple positions at the same time, and when you do it enough times, then you have a really good approximation of the model that you're looking for. Any questions?
Could you please expand that figures a little bit more?
These.
What's the yellow rectangle means?
Oh, it's just highlighting the update. So at this time step, you're basically updating 3 spots. So you have a random distribution, right? You have a mini batch. You took random samples in those, from your entire dataset, you took some random samples and formed a mini batch from it. And you update the network at these spots. So basically, when you're updating the network randomly, when you do it iteratively, eventually you end up having a nice approximation of the model function you're looking for. Right? Yeah.
So I guess the red line is the true function, and the dot line is like
The blue line is the true function that you're trying to model. The red line is so basically the red lines signify the changes that are happening with the updates. Yeah.
So do the chosen subsets, do they have to be disjoint and be total up to the training set?
Yes. So basically, when we are sampling data from the data set, the training set, we ideally would want the data to be statistically independent. There is no dependencies between the data, and they are completely random. So you keep doing that iteratively. You pick random samples over many times, and you keep training the data, and eventually you end up with the approximate function. Yeah.
So why is mini batch better than the whole batch of all dataset?
So whole batch, firstly, it is computationally expensive. It takes a long time to compute all of that. And secondly, it's like you're trying to train the entire network at once. So the handkerchief example that I've given, you have a function, you're trying to pick points there, push points down. What if you try to pick all of those points at once? So this is like a synchronous update, and you're not really factoring the updates given by other samples before you update from different samples, right? It's like, So if you update all of the points at once, it seems like not an optimal solution, right? You're trying to pull all of those points up at once. So if you keep updating it in batches randomly distributed, so it kind of tends to give you a better convergence. Let's see. Yeah. So one of the biggest reasons it's computationally really expensive. It takes a long time to get through a network. Yeah.
Does the mini batch algorithm
I can't hear you. I can't hear you.
does the mini batch algorithm make it easier to parallelize the computation, or?
So the computation is anyways parallelized in the GPU, but one of the biggest problems I see with the batch update is basically if your data set is too large, you can't run it through your GPU. So it's impossible for you to run an entire. So in the next assignment, you'll be probably working with 60 GB of data. So how would you fit in 60 GB of data on the GPU? You can't, right? So basically, mini batch works. You can take small samples randomly, and then you can keep updating your data set. So this is the convergence graph for different methods, that is SGD, mini batch, and the batch gradient descent. As you can see, there is not much difference between the convergence of a batch and mini batch gradient descent, except that this is way faster than the batch because of smaller sample size. Yeah, another thing is in a mini batch gradient descent, you have smaller samples which represent your entire data set. So they are picked randomly. So I think that is also one of the causes for it to converge very fast. So you don't have to have a lot of samples to represent your data set. You can have a small number of samples, and you can keep doing it iteratively until you get the final function. Yeah, so we spoke about convergence. Firstly, having a fixed learning rate is not going to help because it's going to diverge some point. What is optimal at one state of training is not going to be optimal at the final state. So you have to find a way to keep updating and changing the learning rate so that every dimension can converge correctly. So one way is to keep decaying the learning rate with the number of iterations that are happening. So we spoke about how how the learning rate can be decayed by inverse proportionality relation with the number of iterations. And then we will be speaking about some adaptive methods, ADAGRAD, ADAGRAD, ADAM, and other ways in which we can optimize, in which we can train the networks. So in our last class, we spoke about momentum, where we keep a running average of all the gradients that we have in the past for every dimension, and then based on those updates, we decide whether we have to take we have to update in that direction or not. For example, if the network has been having having the same gradient, or if the gradient hasn't been changing directions very often, so you can increase the momentum in that direction, because there is still time until the dimension or the weight changes, the gradient changes its sign, right? I'm sorry, did I explain correctly? Did you get it? I'm sorry. So here you can see that the state initially, it is trying to move towards the optimum. So you can see it as two dimensions. You have an x and a y. So it doesn't really make sense if you update a lot in the y direction, because your gradient is mostly towards the x. So here your learning rate increases in the x direction, whereas in the y, because if by increasing it, you will be losing momentum, I guess. You'll not be updating in those directions. Yeah, this is what I was trying to describe. So in the y direction, there is a lot of movement. Therefore, there is little momentum because the gradient has been shifting. And then in the x direction, the gradient has been pretty stable, so there's a lot of momentum, and you can increase your learning rate in that direction. And then we spoke about Nesterov's gradient, accelerated gradient, where you take a step ahead, look how the gradient is, and then based on the gradient in the new state, you take a sum of vectors and you move in that direction. This can also be applied to the incremental updates. So more recent methods have been into understanding how the gradient shifts work and how we could use the information that we get from the change in gradients, the directions, to improve the learning rate, to improve the learning. So ADAM is very popular in this practice. RMS prop is what we are going to be talking about, root mean square. And then all of these are basically versions of RMS prop, so we won't be looking into the other ones. Yeah, so the whole point again comes down to this, to decrease the oscillations and just smoothen the convergence towards the optimum. So one of the ways is RMS prop, wherein you just take the gradient and then you square it. Then the mean squared expectation of this gradient gives us the running estimate. And based on this, we know if the network is diverging or if the network is converging to a spot. So, if there has been a lot of oscillations in one dimension, you basically don't move in that direction. And if there is little oscillation, then you probably just move in that direction. Yeah, so this visualization gives us an tells us how each of these convergence methods work. So SGD, as you can see, is very slow in converging to the optimal, whereas the other momentum methods and NAG pretty much get there as quickly as possible. So there have been different ways. So this doesn't mean that SGD never works. It's just that in this case, SGD is very slow to converge, but sometimes SGD tends to work. So you have to run it. You have to try it. It's completely empirical. Whatever works for you is going to work. Yeah. And this is how it works in a saddle point. You see, SGD takes forever to converge. So you can think about something here. So SGD is slow, right? So it might not be correct to use SGD from the start. So you can probably just use an atom in the beginning, and when your network stops converging, you can just switch with an SGD and with a very low learning rate and see if you can improve your results with it. Yeah.
One SVD, like the step SVD takes is very small.
Yeah, we have a lower.
Here shows.
I'm sorry.
I mean, while the SVD, like each step it takes is very small.
Yes.
But why? We can achieve like I can understand like if SVD's direction is kind of noisy, but this one just shows it moves slowly.
I'm not really sure of what the parameters, what the learning rate was when they were doing it, but it actually signifies how each of these networks work. SGD is usually slow when you're running it with, training your networks with it.
So is the idea that SGD is slower because it never it doesn't recognize that the gradient's still increasing in the same direction and accelerate the learning?
So you can look at SGD as a very naive algorithm. It just keeps shooting at the minimum. So you see, here SGD is stuck in a local minima. So that is because it is not looking for anything else. So I don't think it will ever get out of that pace. But yeah, SGD 10.
Recognize that the gradient's decreasing more in some certain direction or some other heuristic and start moving.
So you can also attribute it to this, right? So because the learning rate is fixed, no matter what you do, how fast you move, sometime you get into a local minima, you can't get out of it. So there is no way for you to move out of local minimas because you're always shooting towards, you're always shooting with the fixed learning rates. Sure. So if you have a learning rate which is adaptive, which keeps changing, then probably you can start off with a larger learning rate, explore areas, and then move into global minima, I guess. Yeah.
So I guess for these examples, they are all, the batch size is all 1, is it?
I'm sorry?
I mean the batch size here.
The best size?
When computing like the gradient for the momentum, is it only use the one sample to compute the gradient or a mini batch size?
I'm not really sure what they used, but you can expect similar results. It doesn't really matter. The convergence is not really dependent on the algorithm that you're using, whereas so the convergent is dependent on the algorithm that you're using, whereas the variance is dependent on the sample size.
Yeah, because the reason why I ask curious about it is that other algorithms has the right direction, while SVD don't have the direction.
Yeah, so it is stuck in the local minima, right?
Yeah.
So it is not trying to explore areas.
So why these methods can get rid of the local minima?
So I think I'll just have to refer to that paper to see what parameters he used. Can't really answer without it. So, but you still get the idea, right? What happens? Just for intuition, if you ever feel that your network is stuck in a local minima, you can probably try changing your the method that you're trying to use. Either use an atom or another optimizer to see how it works. So the whole point of optimization here, the class here, is basically to help you with homework part 2. So the divergence. So how do you decide what divergence to use? So the network is converging based on the error, right? So the error is backpropagated through the entire network. So what loss function is optimal for your network is one of the questions that you should be looking into. And also, what kind of function are you looking at? So which ones do you think is a better function to model? I mean, better function to optimize? Is it, obviously this one has a lot of local minimas, and this one has a global minima, but it is steep. Any function with a steep gradient near the minimas is not really good. And then we should be aiming at having a smooth, we should be looking at having a smooth function. which helps us having a nice divergence. Steep gradients is usually bad. Smooth curves is usually good. That's the intuition that you have to take from this. So again, what happens if you have a steep curve is, suppose you're using an SDD, you have a fixed learning rate, you just get into it, you overshoot and you get out of it. So there is no way, or it is really difficult for you to converge to an optimum. Whereas if you have a smooth curve, it is very easy for you to get down. So the most common functions that we use for loss for divergence are L2 and the KL, Kullback, Lieberman, KL divergence. So L2 divergence is basically used for numerical prediction. So you are trying to predict values like linear regression or maybe. So then L2 works, and KL divergence works very well for classification methods, because it basically deals with probabilistic outputs. Yeah, so here comparing L2 and the KL divergence, which one do you think is a better function? So both of them have both of them have a global optima, but as you can see, L2 divergence has a steep gradient just close to the minimum, whereas the KL divergence has a really nice smooth curve before it gets to the minimum. So everyone has implemented batch norms, right? So while implementing, have you ever thought about visualizing what effects that batch norm is having on the data? So let's look at mini batch updates. So this is what we are trying to. So we are assuming that the mini batches have a very similar distribution. So each of these colored blobs, assume each of these colored blobs are mini batches, is a mini batch. But usually that is not the case. So it's not really random. Even though you are picking those samples randomly, there's always some biases inside that. So it is not very well distributed. So this is more or less what you can expect. Your data, each of your mini batch has variances inside them. So it's not very similar to each other. And this is the worst case. You can have completely different samples in each of your mini batches. So what we try to do here is we try to normalize the data that we have. So each mini batch should more or less be similar to other mini batches. This is because you want the network to learn from very similar things. It should be random, but it should have very similar data. Yeah. So basically, what you do is you try to mean all the data. You try to center the data. It's basically called a zero mean method. Yeah. So you just subtract the mean and you divide the data with the standard deviation, the variance. So this is what you should be expecting. This is an ideal representation of mini batches. So you don't have any biases inside them. A mini batch is really nice. I mean, it is zero mean. You don't have a separate mean for each of them. And then you scale and shift it. So this is also called a covariate shift. This is to, again, normalize the data that you have so that the network is trained correctly. So yeah.
Where do we move the data to?
Yeah, so it is called scaling and shifting. We'll just get to that in a second. So you don't know exactly where to move it. That is another parameter that the network is going to learn. So batch norm has all of these parameters. When you're implementing it, all of it is being learned. So you don't know it when the training starts. So ideally, where do you think the batch norm should go now? Before activation, right? Obviously, because you don't want any additional factors to creep up after your activation. So you basically zero mean it, you use batch norm, and then you pass your outputs after batch norm into your activation layers. And you don't do it in the final layer, you only do it for the layers before it, because the final layer is basically a logits layer which gives you the probability distribution of the outputs. So again, so batch normalization has two parts. The first part is zero mean and zero mean and shifting, scaling and shifting. Sorry, the first part is only zero mean and you normalize it, and the second part is scaling and shifting. So this is what you do. You use a covariate shift to the standard position, and then you have your scaling and shifting, what we just saw. So this is what happens in the first part. You have your covariate shift, you normalize it with your standard deviation, and then you scale your batches, and then you shift it. And then obviously you do it for your entire batch. So your variance becomes your summation over the batch divided by it, and also the mean changes. So two parts again, right? Firstly, we are introducing two variables here. Gamma is your scaling factor. So basically, you have your mini batch. You have to move it somewhere. So how would you decide how much to scale it? And then you have your beta, which is basically telling where to move it. So the shifting factor that we're using. So how do we do backpropagation through batch norm? So the first part is very simple. You have your outputs. You have your divergence function, change in divergence with respect to your output, and then it just keep backpropagating, and then you have your change in divergence with respect to z. And what gets interesting is what happens inside this. So the second part of the batch norm is pretty easy. You just have to do the divergence, the change in divergence with respect to the shift factor and the scaling factor. It comes in very directly from this. Just differentiate and you get those outputs. Whereas the first part is a bit more complex. How would you know the change in divergence with respect to z? Right. So z is influencing not only the covariant shift, but also u. So yeah, so you can see z, the mean, the variance, and the output from the first part of the batch norm is dependent on the z. So therefore, all of that should be factored into the backpropagation. So this gives you the final equation, and I'm sure everyone has already implemented it. Yes.
What's mu sub b and ui?
Sorry.
In this equivalence diagram, what are those?
Mu is the mean. The mean.
UI, is that the normal?
U is the output from the covariate shift. So you have the two parts, right? You have the covariate shift in the first one, then the output from it, and then you do a scaling and shifting.
X hat in the so.
Sort of. Sorry?
Sorry, did you say sort of?
So that is the output from the first part of batch norm.
Yeah, before you scale it.
Yeah, exactly. Yeah.
Yeah, so in the homework part 1, that's called X hat, and then Y is the scaled version.
Yes.
Yeah, great, thank you.
Sorry, I'm not dealing with part 1, so. So another thing with batch norm is you freeze the variables that you've learned during the training, and you don't change them during inference. You just assume that is your mean, and those are the covariant shift and your scaling and shifting factors that you're going to use for your entire data set. You assume that the incoming data also has similar characteristics, and then you don't have to retrain it. Yeah.
So I was looking over last year's slides and trying to implement batch norm in my homework.
Mm-hmm.
It doesn't feel like the alpha update that we used in the homework is the same as this. I'm sure it is. Could you explain how this is similar to the
homework
update that we made using alpha in our homework?
That's at test time. So the idea is that how do we do normalization at test time? This is in training. So during evaluation, imagine that you have a single sample. How do you represent the statistics for normalization? What's the variance of a single K example? So the idea is to maintain a representative statistic that you can then use at test time. So
So, but is this a different method? We used like the previous running mean multiplied by alpha times the current mean multiplied by 1 minus alpha in order to do our update for the running mean. Is it the same as this?
We're not doing that here.
Yeah, we're not doing that here.
So
That's mostly the question is it the same? Like, is this step equivalent to what we were implementing? Because this is like almost saving all of the means and then taking the average of them across all of our iterations.
This is something different.
Yeah, that's one.
We'll just clarify this on Piazza. Probably just talk to the
Great.
professor.
That sounds great.
So the results with batch norm are typically way better than what you would get without a batch norm. So that is what this graph signifies. Okay. So everything that you have seen till now might not be accurate because you never have the complete sample. You do not have the entire sample set to model the function exactly as it is, right? So you have some samples, there is some overfitting, and this is typically what you get if you have a very sparse sample set. So you are only training the model at certain samples, so it tends to overfit, and it is not very well extrapolated between the points. So this is the reason we use some smoothing methods. Okay, we'll just get to the smoothing in a minute. So again, I just spoke about how we have so many dimensions, so many parameters, and we would be needing so many samples to train the network accurately, but we don't have those samples. So here is another example. Suppose you have a 100-dimensional data set, 100-dimensional input data. You have, suppose it is binary. You have 2 power 100 possible inputs. So for all of those inputs, if you want to accurately approximate the function, you need all of those samples, right? So you don't have all of those samples. You basically have a very sparse sample set, and it's very difficult to get a good method without using smoothing. So this can be, we can think of it like this. You gave it a dot and you're asking the network to approximate a function over it. It's impossible unless you have enough functions. So we can add in a few smoothing constraints basically where you tell when the weights are becoming too high. You tell the network that the weights are becoming too huge, and you add a regularization parameter that doesn't allow the network to increase the weights too much. So the parameters, regularization parameters, basically keep the weights in check. So this is the kind of function we want to approximate. So you have your training samples. So we ideally would expect a smooth curve from between all of these samples. But what you get is something very similar to this. This is a classic case of overfitting with a binary classifier. Yeah. And this could also be said because individual neurons are very good at detecting edges, and becomes really difficult for you to. We'll get to that in a minute. Sorry. So yeah, another thing is. Yeah, so this is where we use the regularization parameters, the lambda. So we basically control the size or the size of weights with lambda. So if your weights are increasing, the lambda decides whether you reduce the weights or not. So if you have a greater lambda, if you have a larger lambda, it gives importance to shrinking the weights, because in the end you're still trying to minimize the loss function. If you have a larger lambda, you cannot have bigger weights, because having bigger weights would in the end mean having a bigger output for the loss function. Yeah, so this is pretty much a summary of what the update should look like for the batch, stochastic mini batch, and the update rule for, this is the stochastic update rule, yeah. So this is a summary of what we've discussed, and we'll probably just be adding a lambda w at the end. So it's not going to change a lot of, it's not computationally intensive, it's just adding another parameter at the end. So we can also control the smoothness through the structure of the network. Example, if you have a single layer, all the network learns is to draw edges, right? Each perceptron basically can draw a single edge. So deeper representations usually have a much smoother output. For example, let's look at this. Let's look at the results for this. So basically, we are trying to estimate the contours for this. So let's find a better example. Yeah. So you have the input shape to the left, and you have 660 units in total. So initially, with 3 layers, the output is very bad, and then when you keep increasing your layers, the output keeps improving. So why do you think this happens? So basically what happens is when you have a stack of layers, when you have layers stacking over one another, layers on top tend to learn much more complicated features as compared to layers at the bottom. So the layers at the bottom can only understand lines, whereas when you keep increasing the depth of it, it tends to learn much more complex features. And here you can see the output of the bear, which more or less looks like a bear here, and it's just rubbish with 3 layers. Any doubts here?
Question?
Yeah.
So on the layers, we know that it increases with number of layers. Does it matter how many, like, is there a relationship with the number of nodes within each layer? Or are these assuming like equally
So
wide layers, I guess?
I don't think it really depends on the number of units, as long as it is not too less. Because if you're just stacking, so like honestly, I don't think there's a rule for that, having the fixed number of layers, fixed number of units per layer. But the general understanding is that if you keep increasing the depth of layers, you can model much more complex functions. Do you have anything to add?
Yeah, I was just going to say, we assume that there's enough capacity
Yeah.
in the network at each of these layers to learn the representation. I believe it's saying that it becomes easier to learn
Exactly.
these more complex decision boundaries here with more layers, even if we had the enough capacity beforehand.
Yeah.
So
Yeah.
if you're actually going about trying to build a model that's going to fit something like this,
Mhm.
would you first try increasing the number of units per layer before you start adding layers? Or like what direction would you start experimenting
So
with that?
I usually tend to do this. I first try to overfit the model. Once you know that the model is learning, and then I keep reducing the number of units per layer to see what works best.
So when you say overfit, you mean add more layers?
Units. Both. I mean, it's all empirical. Whatever works for you should do. And there is no golden rule telling you to do it in a certain way. You can just keep trying it until something works. Anything to add? Okay. So we've discussed a couple regularization techniques, but one of the most prominent ones that have shown to give really good results is the dropouts. So dropout is basically just switching off some units while you're training it, so that the network can learn much more complex and much more denser representations. So this is under the understanding that the network has enough capacity again. So if the network is full to capacity, if the network perfectly models your function without having any extra space, then if you switch off the layers, it's not going to work. You need to have extra capacity. You can, yeah.
Sorry, and does the dropout, when they say drop out 50% of your units
Yes.
at
Mhm.
a given layer, is it doing that for just that batch size, or is it changing what neurons it's turning off in each batch, or is it doing it for the entire epoch? How does that function?
The idea is that for each sample that you feed forward, treat each unit as a Bernoulli random variable, each weight, and you include that weight with that, whatever, if it's 0.5 to 50% of the time, it's like flipping a coin with a bias for each weight.
So they could be changing a lot, basically is what you're saying. Like, is this with each batch, you flip a coin and then turn on those weights for that batch and then back propagate?
I believe that's how it's most easily implemented, is over the batch.
And we are not switching off the weights, we're switching off the entire neuron. So it's not an edge that you're switching off, when you turn off a neuron, all of the weights that are coming out of it are gone. So there are methods where we switch off weights as well, each edges, but we're not going to be discussing it. So why do we think dropout works? So basically, we have this method called bagging, where we use an ensemble of classifiers. We use a lot of classifiers. We train it, we propagate it. Once we get the results, we basically poll, vote, and then we pick the best results, and that is our output. So this tends to give us, this showed really good results because we have a lot of different ways in which we are training and a lot of different networks, which might give different answers based on probably random initialization or whatever it is. But this has shown to give us really good results. So this leads to dropouts, where you try to model all of those different networks into one network. So this is the base network that you have. And then you keep dropping off layers, neurons. Drop out 50% of it. And then, yeah, so one network can be represented as 3 different networks here. That is because you have a different structure for all of them. You're dropping off certain neurons, certain perceptrons. Therefore, it kind of tends to learn a lot of dense it learns a dense representation of the function, basically. Yeah, so again, it's the same thing. So if you have n neurons, there are 2 power n different ways in which you can model the function, possibly possible subnetworks. So basically, one network can represent 3 networks. That is what, can you put it in different ways?
Yeah, I mean, it is sort of what it's saying on the slides here is that you're effectively averaging over different possible networks. It's sort of like implicit bagging.
Yeah.
In a way.
But the less capable networks, like averaging over less capable networks doesn't guarantee that it'll be better than one more capable network.
It's why it's regularization, right? You're actually impeding the representational ability, but you're allowing it to not overfit.
But are we also assuming that like even after the dropout, the network still has the capacity to model what needs to be? Or
Yeah, so basically when you're dropping off neurons while training, the network tends to learn new ways, new connections in which it can classify or produce results. So this kind of leads to having a much richer probability, much richer pattern density, and it works. It tends to work better. So these are typical results with dropouts and without dropouts. So as you can see, the network performs way better when you have dropouts. So once people got to know that dropouts started working, they came out with various versions of it. Zone out, where few of the units are not updated, and drop connects where edges are dropped, and some other methods. In the end, it's all the same. You're still trying to learn different representations with the same network. Yeah, some other ways in which you can see if stop before your network starts overfitting is by plotting the graphs of validation and training accuracy or error. So basically, if your validation error starts increasing, that means that your network started overfitting and you just stop training at that point. So we will be going over how you can do this using TensorBoard in the next recitation. So for now, yeah, this is the intuition. Once the validation error starts increasing, you just stop training it. Yeah, and there is another method in which you can regularize, that is gradient clipping. So once your gradients start increasing a lot, probably just getting to infinity, sometimes your networks, when you're training, starts giving you zeros as the outputs. That could be because of zeros or infinities as the outputs. That could be because of the gradients increasing exponentially. So what we do is we just have a fixed size theta. So once your gradient increases that value, you just clip it. So it's usually taken as 5. But yeah, you get the intuition, right? If the slope is too much, you just stop increasing the weights anymore. You don't go above that. You don't update it when it goes above it. Yeah, other ways in which you can regularize, this is specifically done when you have a smaller sample set. You augment the training data. So if you're trying to learn a function and you feel that you don't have enough samples, you do tricks like rotating it, distorting it a bit, changing the sizes of it. This increases your data set as well as improves the training, because each of these different orientations are treated as different samples by the network. So there are some other ways in which you can improve the training. We'll be speaking about some methods, the ZCA methods in the next recitation. So yeah, so in the end, it's all about normalizing the inputs, making sure the data is as standardized as possible. There are no biases that the samples can induce. So I think all of you have already gotten to this point. So initially, to set up any training algorithm, to train any algorithm, firstly, you need the data set. Without data set, you can't really do anything. Then you choose your network architecture. Just start somewhere. It's OK if the network seems too big. Just see if it is learning, if it is overfitting. If it does, then you can start tuning your parameters. You can just decrease the size, see what works, see what doesn't work. Yeah, so you can use deeper networks based on, if you're using it on your personal computer, it depends on your RAM, the GPUs. If you're using it on AWS, it depends on your credits. So just start with the larger network, keep reducing it, see what works. It's all empirical, whatever works for you should do. And then you have to choose the right loss function. Start with cross entropy. Are there any other loss functions at work? Just start with it, keep looking into it. Then you sometimes batch, at least for part 2, batch num definitely works. Dropouts might or might not work, so you'll have to check that as well. It's important about understanding where dropouts should be placed. So just keep trying it. Dropouts are usually placed in the starting layers so that you have different connections from start to end. But then it again depends. And optimization algorithm, again, I spoke about how you can use Adam initially, and once your training is saturating, once the error doesn't decrease anymore, you can probably start using SGD with a very low learning rate. So intuitively, it makes sense, right? SGD is like a naive algorithm. It just keeps hitting towards the goal. So if your training is saturated, there is nothing more that your Adam or whatever optimization that you use is going to do. Then you can just try it out. If it works, it works. Else you can just try for something else. And yeah, you just keep tuning your parameters and just keep working until it works. So this is going to be a norm for all of your assignments from now. It's going to be a lot of trial and error until you make it. Yeah. So that's about it. That's the class for today. Do you have any questions? Yeah.
When you said just like start with a big network.
I'm sorry?
So when you were talking about choosing your network architecture, right?
Yeah, so that is my opinion. You can do whatever you want to, but.
Do you have like what's too big? Like is 5 layers of 20 neurons too small?
It's definitely application dependent.
Yeah.
Dependent on the kind of how much data you have, the dimensionality of the data.
Yeah.
The task itself, if it's a large, if it's M-way classification, depends how big N is.
Yeah.
But generally, the idea is to try to train a small enough network as you can, see what you can achieve, and then move on from there. A lot of the time, if you have too much capacity, it can take long to learn, and you don't know what's really possible. So it's usually best to start with a small network, saturate the performance on that, and then you can try increasing depth, and also units.
Yeah. So if you've got some number of classes that you're classifying over, is that like an appropriate starting point for
It's also just intuitive, right? If you have 1,000 classes and you're using 3 layers, each with 64 units.
Yeah. It's not. Yeah.
There's a combinatory to that. That's kind of tough. So
yeah.
Sort of thinking that way. But if you only have a 10-way classification problem, maybe 3 layers with 64 units each is fair to start with.
Yeah. So kind of some factor of kind of the number of classes you've got, how big your output is.
Yeah.
So in the end, it depends on what you want to do, right? So I basically prefer larger networks because I have the GPU resources for it. And I can see So yeah, I have my personal computer, so I don't really mind working it all night. So once I see that the network overfitted, the validation error is increasing and the training error is decreasing, then I know the network is learning something. Then I start chopping off layers, chopping off units to see what works best.
Yeah, so the validation error starts.
Exactly. So that's really good metric to know where you have to stop training it.
Thanks, Joe.
Thank you.